Venus is closer to Earth than Mars. It's roughly the same size as our planet. Launch windows open more frequently. Flight time is shorter. Yet every space agency that's ever existed has chosen Mars instead. That seems backwards, doesn't it? We've sent 3 rovers to Mars that are still driving around right now. We're planning human missions. SpaceX wants to build a city there. Meanwhile, Venus gets maybe 1 mission per decade, and those spacecraft die within hours of arrival. The last time NASA sent anything to Venus was 1989. There's a reason for this choice that goes deeper than you think. It's not just about distance or difficulty. It's about something fundamental that determines which worlds humans can actually explore and which ones will remain forever out of reach. Let me show you what's really happening here. Start with the obvious problem. Venus has a surface temperature of 464 degrees Celsius. That's hot enough to melt lead. The atmospheric pressure down there is 93 bars, equivalent to being 900 meters underwater on Earth. The air itself is 96.5% carbon dioxide, and the clouds are made of sulfuric acid. When the Soviet Union landed their Venera probes on Venus in the 1970s and 80s, those spacecraft survived for maybe 2 hours before the environment destroyed them completely. They managed to send back a handful of grainy photos showing a rocky, desolate landscape, then went silent forever. Compare that to Mars. Surface temperatures range from minus 133 degrees Celsius at the winter pole to a relatively balmy 27 degrees Celsius during summer. The average sits around minus 55 degrees Celsius. Cold, yes, but not impossible. The atmospheric pressure is less than 0.01 bar, basically a vacuum. But that creates different problems than crushing pressure. Problems we can engineer around. The Spirit rover landed on Mars in 2004 with a planned mission duration of 90 days. It operated for 6 years, driving over 7.73 kilometers and sending back thousands of images. The Opportunity rover, Spirit's twin, was supposed to last 90 days as well. It survived for 15 years. You can't do that on Venus. The environment simply won't allow it. But here's what makes this interesting. Venus wasn't always this way. About 4 billion years ago, Venus might have looked remarkably similar to early Earth. Scientists speculate it had liquid water on its surface, possibly oceans. The atmospheric pressure and temperature were likely far more moderate. Venus, Earth, and Mars all started with roughly the same ingredients, similar distances from the Sun, similar compositions, similar potential for habitability. Then something catastrophic happened on Venus. The leading theory involves a runaway greenhouse effect. Venus's proximity to the Sun meant slightly more solar radiation hitting its surface. That extra heat caused more water to evaporate from the oceans. Water vapor is a greenhouse gas, so it trapped more heat, which caused more evaporation, which trapped more heat. The cycle accelerated until every drop of water had boiled away into the atmosphere. Then the water molecules broke apart from intense ultraviolet radiation. Hydrogen escaped to space. What remained was an atmosphere of almost pure carbon dioxide with clouds of sulfuric acid, creating the hellscape we observe today. Mars went the opposite direction. It's smaller than Earth and Venus, only 11% of Earth's mass. That matters more than you might think. Smaller planets cool faster. They lose their internal heat more quickly. Mars likely had a thick atmosphere early in its history, and evidence suggests it was covered with liquid water. The Odyssey spacecraft found geological features that look exactly like ancient ocean basins. Dried river valleys snake across the surface. Minerals that only form in the presence of water sit exposed in Martian rocks. But Mars couldn't hold on to that atmosphere. Its magnetic field weakened as the core cooled, allowing solar wind to gradually strip away the gases that kept the planet warm. The water froze into the ground or evaporated into space. Mars became the cold, dry desert we see today. Yet here's the critical difference. Mars preserved its history. Venus's geological record was erased by the runaway greenhouse effect. The surface was resurfaced by volcanic activity. Any evidence of ancient oceans or past habitability is buried under kilometers of volcanic rock or destroyed by the extreme conditions. You can't study what you can't access, and you can't access anything on Venus's surface for more than a few hours. Mars, by contrast, is a planetary time capsule. The lack of plate tectonics means 4 billion-year-old rocks sit right on the surface, waiting to be examined. No erosion from water or wind has worn them away significantly. No geological recycling has pulled them back into the interior. When the Curiosity rover drills into Martian rock, it's sampling material from the ancient past, analyzing chemistry that tells us what conditions were like when the solar system was young. We can trace the history of water on Mars by looking at the layers in canyon walls. We can study how the climate changed by examining different rock types at different elevations. This is what scientists call comparative planetology, and it's one of the main reasons Mars receives so much more attention than Venus. Mars can teach us about Earth's past in ways Venus simply cannot. If we want to understand how planets evolve, how atmospheres change, how water appears and disappears, we need to study the geological record. Mars has that record. Venus does not. But there's another factor at play here, one that might be even more important than scientific return. Mars has the potential for something Venus will never offer. The possibility of finding life. Not intelligent life, not little green men, but microbial life. Single-celled organisms, bacteria-like creatures that might exist in the Martian subsurface where conditions are less hostile. We have strong evidence that liquid water still exists on Mars today, trapped beneath the polar ice caps and possibly flowing through underground aquifers in certain regions. Where there's liquid water on Earth, there's almost always life. The question isn't whether life could theoretically exist on Mars. The question is whether it actually does. This possibility drives enormous amounts of funding and public interest. NASA's Planetary Exploration Program emphasizes the search for life or conditions that could support it. That focus puts Venus at a severe disadvantage. There's virtually no chance of finding life on Venus's surface. The temperature alone would break apart any organic molecules. The sulfuric acid clouds would corrode any biological structures. The pressure would crush any cellular membranes. Venus is, by any reasonable definition, completely sterile. Some scientists have proposed that microbial life could exist in Venus's upper atmosphere, floating in the cloud layers where temperatures and pressures are more moderate. It's an intriguing hypothesis, but it requires life to exist permanently suspended in the air with no access to solid ground or water sources. That's far more speculative than the idea of underground microbes on Mars using subsurface water ice. When funding agencies decide which missions to support, they lean toward the scenarios with higher probability of success. The engineering challenges tell a similar story. We can put a probe in orbit around Mars, and it will last almost indefinitely, observing the surface through a thin atmosphere, tracking weather patterns, measuring geological changes. We can land a robot on Mars knowing it won't be crushed, melted, or corroded within hours. The solar panels will work. The electronics will function at cold but manageable temperatures. Communication with Earth is straightforward because Mars's thin atmosphere doesn't interfere with radio signals. Venus requires completely different technology. Any lander needs extraordinary heat shielding and pressure resistance. Electronics must be specially designed to operate at extreme temperatures, which typically means they can only function for brief periods before failing. Solar panels are useless because the thick cloud cover blocks most sunlight from reaching the surface. Communication through that dense atmosphere is difficult. You can't see the surface from orbit, which makes selecting landing sites challenging. Every aspect of a Venus mission is harder, more expensive, and produces less scientific return per dollar spent than an equivalent Mars mission. Consider the cost-benefit calculation from an agency's perspective. A short-lived Venus lander that can only analyze its immediate vicinity might cost the same as a Mars rover that can drive around for years, examining dozens of different sites, drilling into various rock formations, covering kilometers of terrain. The Mars mission will generate vastly more data, more discoveries, more publications, more public engagement. It's not that Venus isn't scientifically interesting. It absolutely is. But Mars offers exponentially better value for the investment. This becomes even more apparent when you think about human exploration. Every space agency with serious ambitions talks about sending humans to Mars within the next few decades. NASA aims for the 2030s or early 2040s. SpaceX wants to build a permanent settlement. These aren't idle dreams. They're backed by detailed mission architectures, technology development programs, and substantial funding. The engineering challenges are immense, certainly, but they're solvable. We know how to build habitats that can withstand Martian conditions. We know how to extract water from the soil. We know how to generate oxygen from the carbon dioxide atmosphere. We know how to grow food in greenhouses using Martian regolith as a growing medium. None of that works on Venus's surface. You cannot build a habitat that will survive 464-degree heat and 93 bars of pressure indefinitely. You cannot extract resources from the ground when the ground is hot enough to glow faintly red. You cannot grow food or establish infrastructure or create anything resembling a permanent settlement under those conditions. Some scientists have proposed an alternative: floating cities in Venus's upper atmosphere. At an altitude of about 50 kilometers above Venus's surface, the temperature drops to around 75 degrees Celsius. At 55 kilometers, it's a comfortable 27 degrees Celsius, room temperature on Earth. The atmospheric pressure at these altitudes is roughly 1 bar, the same as Earth's surface. A habitat filled with breathable air would naturally float at this level because nitrogen and oxygen are lighter than carbon dioxide. In theory, you could have a colony suspended in Venus's clouds, enjoying Earth-like pressure and temperature, protected from radiation by the thick atmosphere above. It sounds almost science fictional, but the physics checks out. You'd get 4 times as much solar energy as Mars receives, which is excellent for power generation. The gravity is nearly identical to Earth's 0.904 g compared to Mars's 0.38 g, which would prevent the health problems associated with long-term exposure to low gravity. Launch windows to Venus occur every 584 days compared to Mars's 780 days, and flight time is shorter. From a purely physical standpoint, Venus's upper atmosphere is arguably more Earth-like than Mars's surface, yet nobody's seriously planning to build cloud cities on Venus, while multiple organizations are actively developing Mars colonization plans. There's a reason for that, and it goes beyond simple engineering preference. Humans need solid ground. We need access to resources. A floating habitat on Venus would have no easy way to mine metals or extract materials for construction and manufacturing. Everything would need to be imported from Earth or asteroid sources at enormous cost. You couldn't expand the colony by building on adjacent land. You'd need to construct entirely new floating structures. There's no bedrock to anchor anything to, no soil to grow food in, no geological resources to tap. You're permanently suspended in a corrosive atmosphere of carbon dioxide and sulfuric acid, with hurricane-force winds constantly buffeting your habitat, and the surface below is completely inaccessible. Compare that to Mars, where you can drill into the ground, extract water ice, build underground shelters for radiation protection, use local materials for construction, and potentially terraform the environment over centuries. Mars offers a path toward genuine self-sufficiency. Venus does not. This difference shapes everything else. It determines which missions get funded, which technologies get developed, which destinations capture public imagination. Mars represents a future where humanity expands beyond Earth in a meaningful way. Venus represents an interesting scientific target that will likely remain exactly that, a target for brief robotic missions, not a destination for human civilization. The Soviet Union understood Venus's challenges better than anyone. They sent more missions to Venus than any other nation, over 20 spacecraft between 1961 and 1984. The Venera program achieved genuine firsts. First successful landing on another planet, first photos from another planet's surface, first analysis of another planet's atmosphere and soil. Those achievements came at extraordinary cost, both financially and technically. Each lander was essentially a one-time use probe designed to survive just long enough to transmit basic data before being destroyed. The Venera landers weren't elegant. They were brute force engineering, heavily armored spheres designed to withstand conditions that would vaporize most spacecraft within minutes. Each mission was essentially a suicide run, a race against time to gather whatever data possible before the inevitable system failure. The last successful Soviet lander, Venera 13, survived for 127 minutes in 1982. That's just over 2 hours. In that brief window, it captured a handful of images, analyzed soil composition, and transmitted atmospheric data before succumbing to the heat and pressure. For comparison, NASA's Opportunity rover operated on Mars for 14 years. Not 14 months, 14 years. It traveled over 45 kilometers across the Martian surface, examining rocks, analyzing soil, discovering evidence of past water, and fundamentally changing our understanding of Mars's history. The Spirit rover, Opportunity's twin, lasted 6 years. Curiosity has been active since 2012 and is still exploring today. Perseverance landed in 2021 and is currently drilling core samples for eventual return to Earth. These missions don't just survive, they thrive. They continue operating years beyond their planned lifespans because Mars, for all its challenges, doesn't actively destroy the equipment sent to explore it. That difference matters more than almost anything else when you're planning missions that cost hundreds of millions or billions of dollars. Venus punishes every probe we send. Mars allows long-term exploration. This isn't a minor technical detail. It's the fundamental reason why Mars has become humanity's primary target for exploration beyond Earth, while Venus remains a fascinating but secondary priority. But there's something deeper happening here, something that goes beyond engineering constraints or mission duration. The real divergence between Mars and Venus exploration stems from what we're actually looking for. NASA's planetary program has a clear emphasis: the search for life, or at least the conditions that could support it. This single priority reshapes everything. It determines which missions get funded, which technologies get developed, which destinations capture public imagination. Mars fits this mandate perfectly. Evidence of past liquid water covers the planet's surface. Ancient river valleys, lake beds, delta formations carved into the landscape. The Perseverance rover is currently exploring Jezero crater, which was once filled with water billions of years ago. If life ever existed on Mars, this is exactly where we'd expect to find traces of it. The rocks Perseverance is collecting might contain fossilized microorganisms, chemical signatures of biological processes, or evidence of habitable environments that persisted for millions of years. These samples will eventually return to Earth for analysis in laboratories equipped with instruments far more sophisticated than anything we can send to another planet. It's not just speculation about ancient life either. Recent discoveries suggest liquid water might exist on Mars today, trapped beneath the polar ice caps or flowing seasonally in certain regions. The South Polar Ice Cap appears to contain ponds of liquid water, briny, extremely cold, but liquid nonetheless. If life emerged on Mars billions of years ago when conditions were more favorable, could it have adapted to survive in these harsh refuges? Could there be Martian microorganisms living in subsurface water right now? These questions drive Mars exploration. They justify the budgets, inspire the missions, capture global attention. Venus offers no such possibility. The surface temperature alone, 464 degrees Celsius, eliminates any chance of life as we know it. No organic molecules could survive intact in that environment. No liquid water exists anywhere on or beneath the surface. The planet's hellish conditions have persisted for potentially billions of years, enough time to erase any evidence of past habitability, even if it once existed. Some scientists have proposed that life might exist in Venus's clouds, where temperatures and pressures are more moderate. It's not impossible. Microorganisms on Earth can survive in extremely acidic environments, and some thrive in conditions we'd consider hostile. But floating microbes in sulfuric acid clouds are a far cry from the preserved geological record that Mars offers. Even if life exists in Venus's atmosphere, we have no clear path to detecting it without long-duration atmospheric missions that current technology can't support. This creates an impossible situation for Venus advocates. They're competing for funding against missions that offer clear pathways to answering humanity's most profound question: are we alone in the universe? Mars missions can directly address this. Venus missions cannot, or at least not with current capabilities. When NASA evaluates proposals, when congressional committees approve budgets, when the public considers where their tax dollars should go, the question of life weighs heavily. Mars offers tangible hope. Venus offers fascinating chemistry and atmospheric dynamics, but nothing that captures imagination the way potential biosignatures do. There's also the matter of what we can learn about Earth's future. Both Venus and Mars began with similar conditions to early Earth. All three planets formed from the same primordial material, started with comparable atmospheres, and existed in the same general region of the solar system. Yet they evolved along radically different paths. Mars lost its atmosphere and became cold and dry. Venus experienced a runaway greenhouse effect and became an inferno. Earth maintained stable conditions for billions of years, allowing life to emerge and flourish. Understanding why these divergences occurred could provide crucial insights into Earth's long-term climate stability. Both planets offer lessons. Venus shows us what happens when greenhouse warming spirals out of control. Mars demonstrates the consequences of losing atmospheric protection and magnetic shielding. But here's the critical difference. Mars preserves its history in accessible form. The lack of plate tectonics on Mars means that 4 billion-year-old rocks sit on the surface, available for direct examination. Rovers can analyze them, drill into them, collect samples that tell the story of Mars's climate evolution in extraordinary detail. These ancient rocks record the transition from a warm, wet world to the cold desert Mars is today. They contain evidence of atmospheric loss, magnetic field collapse, and the gradual desiccation of an entire planet. Understanding this progression helps us understand Earth's climate system, the factors that maintain habitability, and the risks we face from our own atmospheric changes. Venus hides its history beneath impenetrable clouds and a surface that's been resurfaced by volcanic activity. Even if we could send durable landers that survive long enough to study surface rocks, those rocks wouldn't tell us much about Venus's early history. The planet's geology has been reworked too many times. The evidence we seek may simply not exist in accessible form. This isn't about Venus being inherently less interesting scientifically. It's about practical constraints on what we can learn given current technology and reasonable mission costs. Mars offers a clear path to answering fundamental questions about planetary evolution, climate change, and the potential for life beyond Earth. Venus requires technological breakthroughs we haven't achieved yet to provide comparable insights. The resource equation further tilts the balance toward Mars. Water is abundant on Mars, frozen in vast quantities at the poles, locked in subsurface ice deposits, possibly flowing beneath the surface in certain regions. This water is directly accessible. Future Mars missions could extract it, purify it, and use it for life support, agriculture, and propellant production. The Martian atmosphere, thin as it is, contains carbon dioxide that can be processed to produce oxygen and methane fuel through the Sabatier reaction. The soil contains minerals that could be processed into building materials. There's iron for steel production, silicon for solar panels, and various other elements necessary for sustained human presence. SpaceX's Mars colonization plans explicitly rely on in situ resource utilization, using local materials to reduce the mass that must be launched from Earth. The company intends to establish propellant production facilities on Mars, creating fuel for return journeys using Martian atmospheric CO2 and subsurface water ice. This makes Mars missions increasingly self-sufficient over time. Each mission can support the next, building infrastructure that reduces costs and expands capabilities. Venus offers no such pathway. A floating habitat in the clouds has no access to geological resources. Everything must be imported. Every structural beam, every electronic component, every tool and spare part. You can't mine sulfuric acid clouds for construction materials. You can't extract metals from the inaccessible surface below. Even water production, while theoretically possible through chemical processing of atmospheric components, requires complex industrial equipment that must be launched from Earth. The sustainability equation doesn't work. A Mars colony could theoretically become self-sufficient, given enough time and infrastructure development. A Venus cloud city would remain permanently dependent on Earth for essential materials. This dependency makes long-term colonization economically impractical and strategically vulnerable. Any disruption to supply chains from Earth could prove catastrophic. Then there's the psychological dimension. Humans evolved on solid ground. We're adapted to walking on surfaces, building structures anchored to bedrock, growing food in soil. The concept of living permanently suspended in an atmosphere with no solid ground beneath you and no possibility of ever setting foot on a planetary surface is psychologically challenging in ways that Mars colonization isn't. Mars offers the experience of standing on another world, of exploring alien landscapes, of the tangible sensation of being somewhere real and solid. You can imagine hiking across Martian plains, climbing Olympus Mons, exploring the Valles Marineris canyon system. These activities connect to fundamental human experiences of exploration and discovery. Venus's upper atmosphere offers no equivalent. You float in clouds, observing instruments, perhaps viewing the cloud tops from your habitat windows, but never experiencing the visceral connection to place that comes from walking on alien soil. This matters when you are asking people to spend billions of dollars and potentially risk human lives for exploration and colonization. The vision has to inspire. It has to capture imagination and make the risks feel worthwhile. Mars does this naturally. Venus struggles to compete. None of this means Venus isn't scientifically valuable. It absolutely is. Understanding Venus's atmospheric chemistry, its cloud formation processes, its surface geology, and its evolutionary history will provide crucial insights into planetary science. Future missions will undoubtedly return to Venus, equipped with better technology that can withstand the hostile environment longer and gather more comprehensive data. But the fundamental question remains: given limited budgets, finite engineering resources, and the need to prioritize destinations that offer the best return on investment, why choose Venus over Mars? The answer becomes clear when you consider everything together: the engineering challenges, the scientific questions we most want to answer, the resources available for utilization, the psychological and practical requirements for human colonization, and the simple fact that Mars allows sustained exploration while Venus permits only brief encounters before destroying whatever we send. Mars represents a future where humanity expands beyond Earth in meaningful ways, establishing permanent settlements, becoming a multi-planetary species, and ensuring our survival even if catastrophe befalls our homeworld. Venus represents an interesting but ultimately peripheral target that may never host more than brief robotic missions, unless revolutionary technology changes the equation entirely. This strategic choice reflects decades of accumulated experience and practical lessons learned from planetary exploration. Consider the operational reality. When NASA's Opportunity rover landed on Mars in 2004, engineers expected it might function for 90 days. Instead, it operated for nearly 15 years, covering over 45 kilometers of Martian terrain, examining countless geological formations, and fundamentally reshaping our understanding of Mars's watery past. That kind of extended mission duration creates exponential returns on investment. Each additional month of operation means more data, more discoveries, more scientific papers, more trained scientists entering the field, more public engagement, and more justification for future missions. The Soviet Venera missions to Venus, by contrast, provide a stark counterpoint. These engineering marvels represented some of the most impressive achievements in space exploration history. Designing spacecraft that could survive even briefly in Venus's hellish conditions required revolutionary materials, science, and thermal protection systems. When Venera 13 successfully transmitted color images from Venus's surface in 1982, surviving for 127 minutes before succumbing to the extreme environment, it was genuinely extraordinary. But 127 minutes. That's the operational window you're working with on Venus's surface. Not years like Mars rovers, not even days, just hours at most before the heat, pressure, and corrosive atmosphere destroy your equipment. This fundamental operational constraint shapes everything about mission planning and scientific return. A Mars rover can systematically explore its landing site, investigating interesting features as they're discovered, responding to unexpected findings, and adapting its research program based on accumulated evidence. The Spirit rover, Opportunity's twin, discovered evidence of ancient hot springs on Mars, a finding that emerged from extended exploration and analysis over multiple years. You can't conduct that kind of adaptive, discovery-driven science when your lander has a 2-hour lifespan. The cost-benefit analysis becomes obvious when you quantify it. Suppose a Venus lander costs $400 million to design, build, launch, and operate. You might get 2 hours of surface data from a fixed location, analyzing only what's immediately accessible to your instruments in that brief window. Now suppose a Mars rover costs twice that, $800 million, but it operates for 15 years instead of 2 hours. The Mars mission delivers data continuously for over 131,000 hours compared to 2 hours for Venus. Even accounting for the higher initial cost, the scientific return per dollar invested is incomparably better for Mars. This isn't just about quantity of data. It's about the quality of science that extended missions enable. Short-duration missions capture snapshots. Long-duration missions observe processes, changes, seasonal variations, and long-term trends. Mars missions have watched dust devils dance across the surface, monitored how frost forms and sublimes with the changing seasons, observed how dust storms develop and dissipate, and tracked the subtle changes in atmospheric composition throughout Martian years. This temporal dimension of observation is scientifically invaluable and completely unavailable from brief Venus surface missions. The success rate tells its own story. Mars is extraordinarily difficult to reach successfully. The planet's thin atmosphere makes landing particularly challenging, leading to what engineers call 7 minutes of terror during entry, descent, and landing. Roughly half of all Mars missions have failed, but the ones that succeed often exceed their planned mission duration by factors of 10 or more. Venus missions, conversely, have higher success rates for reaching the planet and surviving landing, but they all die quickly once they're there. The engineering is fundamentally different. Mars challenges you to arrive successfully, but then allows extended operation. Venus will probably let you land, but then kills your spacecraft within hours regardless of how well engineered it is. This creates different technological pathways. Mars exploration drives innovation in autonomous navigation, long-duration power systems, radiation-hardened electronics, and remote operation protocols. These technologies have applications beyond planetary science. They advance robotics, AI, materials science, and systems engineering in ways that benefit terrestrial applications. Venus surface missions drive innovation in extreme environment survival, but these technologies have narrower applications because few places anywhere approach Venus's extreme conditions. There's another dimension that rarely gets discussed explicitly, but profoundly influences mission selection: the human element of exploration. Scientists and engineers invest years or decades of their careers into planetary missions. When you're asking someone to dedicate potentially 15 years of their professional life to a single mission, the prospect matters enormously. Working on a Mars rover mission means years of discovery, publication opportunities, career advancement, and the genuine possibility of finding something revolutionary. Working on a Venus lander means a brief burst of activity followed by mission termination. The career incentives align differently. This affects recruitment, retention, and institutional knowledge. NASA's Mars program has developed deep expertise across multiple missions spanning decades. Engineers who worked on Pathfinder in 1997 contributed to Spirit and Opportunity in 2004, then to Curiosity in 2012, then to Perseverance in 2021. This continuity creates institutional learning that makes each successive mission better, cheaper, and more capable. Venus exploration lacks this continuity because missions are so infrequent and brief that expertise doesn't accumulate the same way. The public engagement factor can't be ignored either. Mars rovers capture public imagination in ways that Venus orbiters or brief landers don't. Curiosity's landing in 2012 was watched live by millions. The rover's Twitter account has millions of followers. Children dress as Mars rovers for Halloween. This public enthusiasm translates into political support, which translates into continued funding. Venus missions, being shorter and less dramatic, generate less sustained public interest and therefore less political pressure to fund follow-up missions. Educational impact follows similar patterns. Universities teach entire courses using data from ongoing Mars missions. Students can propose experiments using active rovers, analyze fresh data, and contribute to real planetary science while still in school. This pipeline creates the next generation of planetary scientists. Venus's limited mission opportunities provide fewer educational touchpoints and less opportunity for student involvement in active missions. Consider also the international cooperation dimension. Mars exploration has become a global enterprise with missions from NASA, ESA, China, India, Russia, and the UAE. This international interest creates redundancy, shared knowledge, and competitive drive that accelerates progress. Venus exploration remains comparatively isolated, with fewer nations investing in dedicated missions and less international coordination. The global Mars exploration community shares data, coordinates observations, and builds on each other's discoveries. Venus lacks this robust international scientific ecosystem. The technology readiness level for Mars missions is also substantially higher. We know how to build Mars rovers that work. We've done it successfully multiple times. Each mission builds incrementally on previous successes, reducing risk and increasing capability. Venus surface missions remain in the prototype phase. Each one is essentially experimental, trying to push the boundaries of material science and thermal protection. This higher risk profile makes Venus missions harder to approve and fund. Resource availability on Mars creates another compounding advantage. The presence of water ice, even in subsurface deposits, means that future Mars missions can potentially utilize local resources for fuel production, life support, and construction materials. This in situ resource utilization potential makes long-term Mars exploration and eventual human presence more feasible and sustainable. Venus lacks comparable accessible resources. Its surface is barren of water, and accessing materials from the crushing surface environment would require technology that doesn't yet exist. Sample return missions illustrate the contrast perfectly. NASA and ESA are actively planning Mars sample return, with Perseverance already collecting and caching rock samples that a future mission will retrieve and bring to Earth. This represents the next evolution in Mars exploration, bringing pieces of another planet home for detailed laboratory analysis, impossible with remote instruments. Venus sample return faces vastly greater technical challenges. How do you design a return vehicle that can survive long enough on Venus's surface to collect samples, then launch through that dense atmosphere, all while maintaining sample integrity. The engineering problems are so severe that Venus sample return remains largely theoretical. The geological record preservation on Mars provides yet another crucial advantage. Because Mars lacks plate tectonics and has minimal erosion in its thin atmosphere, rocks billions of years old lie exposed on the surface. Rovers can examine pristine geological formations that preserve evidence of ancient environmental conditions. This makes Mars an accessible window into planetary evolution and potentially into the origins of life. Venus's surface, by contrast, appears geologically young, probably resurfaced within the last billion years by volcanic activity. The ancient history we'd most want to study has been erased by geological processes, even if we could access it through the hostile conditions. The radiation environment, while challenging on Mars, is at least survivable for electronics with appropriate shielding. Mars's thin atmosphere provides some protection, and rovers can be designed with radiation-hardened components that function for years. Venus's surface radiation environment is actually less severe because the thick atmosphere provides excellent shielding. But this advantage is meaningless when the temperature alone destroys electronics within hours. You can't design around Venus's fundamental environmental hostility the way you can engineer solutions for Mars's challenges. Scientific instrumentation faces similar constraints. Mars rovers carry increasingly sophisticated instruments: spectrometers, cameras, drilling equipment, sample analysis chambers, environmental sensors, and more. These instruments can be relatively delicate because Mars's environment, while harsh, doesn't destroy them immediately. Venus landers must prioritize survival systems over scientific instruments, and the instruments they do carry must be extraordinarily robust and simple, because there's no time for complex measurement sequences. This fundamentally limits the science possible on Venus's surface. Mission costs reflect these realities. While individual Mars missions are expensive, the cost per year of operation becomes remarkably affordable as missions extend far beyond their planned duration. Opportunity's 15-year mission meant the annual operational cost became negligible compared to the initial investment. Venus landers have high upfront costs for technology development, but deliver minimal operational duration, making the cost per day of operation extremely high. From a financial efficiency perspective, Mars missions are simply better investments. The trajectory of technological progress favors Mars as well. Each Mars rover has been more capable than its predecessor. Sojourner in 1997 was the size of a microwave oven. Perseverance in 2021 is the size of a car, carries a helicopter, and includes instruments that can detect organic molecules. This progression shows clear advancement toward increasingly ambitious capabilities. Venus lander technology has advanced too, but the fundamental survival time hasn't improved dramatically. Soviet landers in the 1980s survived about 2 hours. Modern proposals target similar durations because the physics of surviving Venus's surface environment hasn't changed. Mars exploration has developed an infrastructure that compounds its advantages with each mission. When Spirit and Opportunity landed in 2004, They benefited from lessons learned by Pathfinder. When Curiosity arrived in 2012, it built on all previous rover experience. Perseverance in 2021 incorporated decades of accumulated knowledge. Each mission informs the next, creating a virtuous cycle of improvement that makes Mars exploration progressively more efficient and scientifically productive. Venus lacks this cumulative advantage. Each Venus mission essentially starts from scratch because the technology that worked in the 1980s still faces the same fundamental constraints today. You can't incrementally improve survival time when the basic physics of the environment remains unchanged. The temperature will still melt electronics. The pressure will still crush components. The atmosphere will still corrode materials. No amount of iteration changes these hard limits. This difference extends to mission planning and risk management. Mars mission planners can draw on extensive experience operating rovers across varied terrain. They understand how to navigate safely, where to take samples, how to position instruments for optimal measurements. This operational expertise reduces risk and increases scientific return. Venus mission planners have no such reservoir of experience because missions are so infrequent and so brief. Every Venus lander essentially flies blind, attempting to gather whatever data it can in the limited time available before systems fail. The human dimension of Mars exploration creates another powerful advantage. Mars rovers have become cultural phenomena. When Opportunity's mission ended in 2019 after 15 years of service, people genuinely mourned. The rover had developed a personality through its longevity and accomplishments. This public connection translates into sustained support for Mars exploration. Venus missions, by contrast, struggle to generate similar engagement. A probe that survives 2 hours on the surface doesn't capture public imagination the same way. But we need to address a compelling counter-argument that Venus advocates raise. At altitudes around 50 to 65 kilometers above Venus's surface, conditions become remarkably Earth-like. The temperature hovers around a comfortable 27 degrees Celsius. The atmospheric pressure matches Earth's surface pressure. This region of Venus's atmosphere offers better radiation shielding than Mars's surface. Earth-like gravity that wouldn't cause the health problems associated with Mars's lower gravity, and 4 times more solar energy for power generation than we receive on Earth. This has led to serious proposals for floating cloud cities on Venus. Breathable air is less dense than Venus's carbon dioxide atmosphere, so habitats filled with normal air would naturally float at these comfortable altitudes. Theoretically, you could walk around inside such a habitat in shirt sleeves, looking out through transparent walls at the clouds of Venus. The engineering seems almost straightforward compared to building underground habitats on Mars to shield against radiation. So why doesn't this change the fundamental calculus? Several reasons become apparent when you examine the details. First, while the atmospheric conditions at 50 kilometers are benign, you're still floating in hurricane-force winds carrying droplets of concentrated sulfuric acid. The habitat exterior would require constant maintenance to prevent corrosion. Any breach in the habitat envelope would be catastrophic. On Mars, a habitat breach is serious, but potentially manageable. In Venus's atmosphere, It means immediate exposure to sulfuric acid aerosols. Second, resource acquisition becomes extraordinarily difficult. On Mars, you can mine water ice from the ground, extract metals from rocks, use soil for construction. A floating Venus habitat has no access to solid materials. Everything must be imported from elsewhere or somehow extracted from the atmosphere itself. While Venus's atmosphere does contain useful elements, the engineering required to harvest them at industrial scales, while floating in acid clouds, presents challenges we've never attempted. Third, the psychological impact of living permanently airborne shouldn't be underestimated. Humans evolved on solid ground. Mars colonists could walk outside in pressurized suits, explore canyons and mountains, experience the satisfaction of standing on another planet's surface. Venus Cloud City inhabitants would be permanently confined to floating habitats with no ground beneath them, no natural landscape to explore, nothing but clouds in every direction. The appeal of being able to walk around in normal pressure and temperature inside your habitat doesn't compensate for never having solid ground under your feet. The research and development trajectory also favors Mars. We've already developed technologies for Mars surface operations, rovers, habitats, power systems, resource extraction equipment. Each mission advances these capabilities. Cloud City technology for Venus would require developing entirely new approaches with no terrestrial analog. How do you maintain permanent floating structures in sulfuric acid clouds? We have no experience base to draw from, no incremental path to get there. Escape capability presents another crucial difference. If something goes wrong on Mars, a return vehicle can launch from the surface. The technology for Mars ascent is well understood. It's essentially rocket science we've mastered since the 1960s. Launching from a floating platform in Venus's dense atmosphere while dealing with corrosive conditions and hurricane winds introduces complications we've never solved. Emergency evacuation from a Venus cloud city would be extraordinarily difficult. The timeline considerations are stark. Mars colonization could begin with current technology. The first humans could land on Mars within a decade if we committed the resources. They'd face enormous challenges, but nothing that violates known physics or requires revolutionary new technologies. Venus cloud cities require solving problems we haven't even begun to address seriously. The development timeline stretches decades beyond Mars colonization. Scientific priorities also drive the Mars focus. The search for life, past or present, remains central to planetary exploration. Mars offers accessible environments where life might have existed billions of years ago or might exist today in subsurface water deposits. Venus's surface has been sterilized by heat and pressure. Its clouds might harbor exotic microbes adapted to sulfuric acid, but this remains highly speculative. Mars provides concrete targets for astrobiology research with proven methods for investigating them. Water availability clinches the practical argument. Mars has abundant water ice in polar caps and subsurface deposits. Recent research suggests liquid water might exist just below the surface in some regions. This makes Mars self-sufficient for water needs. Venus's atmosphere contains water vapor, but extracting it at industrial scales while floating in acid clouds is theoretically possible, but practically daunting. On Mars, you can simply melt ice. The simplicity matters enormously for long-term sustainability. Agricultural potential follows similar logic. Mars offers soil that can be amended for growing crops. You can build greenhouses on the surface, using Martian regolith as radiation shielding and thermal mass. Martian gravity, while only 38% of Earth's, still provides enough force for normal plant growth. Venus cloud cities would need to grow food in floating greenhouses, dealing with hurricanes and acid exposure, with no soil available except what's imported. The agricultural challenges of Mars are manageable. Venus's are nearly insurmountable. The psychological appeal of Mars extends beyond practical considerations. Mars represents a new frontier that humans can walk on, explore, and eventually terraform. The dream of making Mars habitable inspires people in ways that floating cities never will. This matters because space exploration requires sustained public support over decades. Mars has captured human imagination since we first observed it through telescopes. Venus's appeal is more abstract, more theoretical, less viscerally exciting. Mission costs and funding realities reflect these priorities. NASA's Mars program has consistent funding because it delivers results that justify continued investment. The Mars 2020 mission cost about $2.7 billion, but Perseverance could operate for a decade or more, with each additional year costing relatively little. A Venus Cloud City demonstration mission would cost billions to develop, with uncertain prospects for success and limited scientific return, compared to Mars missions that can drive around for years gathering data. Private sector involvement accelerates Mars development in ways unlikely to happen for Venus. SpaceX is actively developing Starship specifically for Mars missions. The company sees Mars colonization as its ultimate purpose. Multiple other companies are developing Mars-specific technologies, habitats, power systems, resource extraction equipment. This private investment amplifies government spending, accelerating progress toward human Mars missions. Venus has attracted minimal private sector interest because the business case is unclear and the technical challenges are daunting. The international cooperation dimension also favors Mars. Multiple space agencies have Mars programs that complement each other. The European Space Agency, China's space program, India's space program, and others all have active Mars missions or concrete Mars plans. This creates opportunities for collaboration and shared costs. Venus exploration remains primarily NASA's domain, with limited international participation, reducing the total resources available and the diversity of approaches attempted. Human factors research further supports Mars focus. We understand how to keep humans alive in space for extended periods. The International Space Station has demonstrated this for decades. Mars presents challenges: radiation exposure, low gravity, isolation. But they're challenges we know how to address, at least theoretically. We can design Mars habitats with confidence they'll protect inhabitants. Venus cloud cities introduce unknown human factors, psychological effects of permanent floating existence, long-term health impacts of living in sulfuric acid clouds, even if protected, social dynamics of communities that can never go outside to solid ground. The argument becomes overwhelming when you consider that Mars offers a potential pathway to making humanity multiplanetary. If something catastrophic happens to Earth, asteroid impact, nuclear war, climate disaster, Mars could potentially preserve human civilization. It's far enough from Earth to be independent, close enough to maintain contact, and potentially modifiable to become more habitable over centuries. Venus offers no such possibility. Even if we perfect Cloud City technology, Venus can never become a true second home for humanity because there's no surface to build on and no realistic way to terraform the planet. This fundamental difference shapes everything. Mars offers something humanity has never truly lost: the ability to walk on new ground, to plant a flag, to build with our own hands. Every Mars mission's success reinforces this narrative. When Curiosity sent back its first selfie from Mars, the world saw a machine on solid ground, not floating helplessly. When Perseverance successfully deployed Ingenuity, the first helicopter to fly on another planet, it demonstrated mastery over a physical environment. These achievements feel tangible in ways that floating platforms never will. The timeline argument reveals another decisive factor. Mars exploration has momentum that Venus cannot match. NASA's Artemis program, designed to return humans to the Moon, explicitly positions itself as preparation for Mars. The Gateway Lunar Outpost will test deep space habitats. Lunar surface missions will practice living off-world. All of this infrastructure development, all of this operational experience directly transfers to Mars missions. Venus gets no such pipeline. SpaceX's development of Starship specifically targets Mars. The vehicle's design parameters, cargo capacity, crew accommodations, life support duration, all optimize for Mars missions. Elon Musk has stated repeatedly that making humanity multiplanetary means Mars, not Venus. SpaceX's entire corporate strategy revolves around Mars colonization. This private sector commitment accelerates Mars development by decades compared to government-only approaches. But here's what makes the disparity even starker. SpaceX plans to send 5 uncrewed starships to Mars in 2026. 5, each capable of delivering over 100 tons of cargo to the Martian surface. This represents more payload mass than all Venus missions in history combined. If successful, crewed flights could begin within 4 years. Venus has 2 missions planned for the early 2030s, both relatively modest in scope. The economics of sustained exploration favor Mars dramatically. Once you've invested in Mars infrastructure, habitats, power systems, life support, additional missions become progressively cheaper. Each successful Mars landing provides assets that support future missions. Equipment doesn't melt after a few hours. Solar panels continue generating power for years. Habitats remain usable indefinitely. This creates a compounding return on investment that Venus simply cannot offer. Consider the scientific research model. On Mars, Curiosity has been operating since 2012, over a decade of continuous science. Perseverance will likely operate well into the 2030s. These long-duration missions allow scientists to refine hypotheses, conduct follow-up investigations, and make serendipitous discoveries that brief Venus missions cannot achieve. When Curiosity detected organic molecules in Martian rocks, scientists could drive back to the site, drill additional samples, and conduct multiple analyses. A Venus lander gets one shot at one location before its equipment fails. The Mars Sample Return mission, currently in development, will bring Martian rocks back to Earth laboratories. This single mission will tell us more about Mars's geological history than decades of orbiter observations. Scientists will analyze samples with instruments too large and complex to ever send to another planet. Mass spectrometers, electron microscopes, isotope analyzers. Venus faces extraordinary challenges for any sample return. The extreme surface conditions mean any sample container must withstand crushing pressure and extreme heat. Launching from Venus requires escaping that thick atmosphere and massive gravity well. The technical challenges make Venus sample return far more difficult than Mars. Educational and inspirational value also matters. Mars rovers have inspired generations of scientists and engineers. Children follow Mars missions in classrooms. Universities design Mars mission concepts as student projects. The Mars Science Laboratory mission generated worldwide media coverage. This cultural engagement matters for sustained space exploration funding. Venus missions, being brief and offering less dramatic visuals, generate far less public excitement. You cannot overstate how important this public engagement is for maintaining political support over decades. The terraforming question, while speculative, influences long-term thinking. Mars could potentially be made more habitable through centuries of careful environmental engineering. Proposals include releasing greenhouse gases to warm the planet, melting polar ice caps to release water, and introducing hardy organisms to begin building soil. Whether these approaches would actually work remains unknown, but they're at least conceivable. Venus offers no such possibility. The planet's extreme conditions and lack of magnetic field mean terraforming Venus would require technology so advanced it borders on science fiction. Mars's rotation period, 24 hours and 37 minutes, closely matches Earth's day. This seemingly minor detail has profound implications for human settlement. Circadian rhythms evolved over millions of years to match Earth's day-night cycle. Mars colonists could maintain relatively normal sleep patterns. Venus rotates once every 243 Earth days. The extreme day length would require artificial light cycles in habitats, adding complexity and energy requirements. More fundamentally, it demonstrates how Mars resembles Earth in ways that matter for human biology. The dust storm problem on Mars, while significant, proves manageable. The 2018 global dust storm that ended Opportunity's mission lasted several months, but perseverance and curiosity weathered the storm successfully. Engineers have learned to design for Martian dust. Solar panels can be cleaned. Mechanical systems can be sealed. Venus's sulfuric acid atmosphere presents no equivalent learning curve. It simply destroys equipment until you develop entirely new materials and designs. Water availability transforms Mars colonization from theoretical to practical. The Mars Odyssey spacecraft confirmed massive water ice deposits at both poles and buried beneath the surface at lower latitudes. Recent research suggests liquid water may exist in subsurface aquifers. This water can be extracted, purified, and used for drinking, growing food, and producing rocket fuel through electrolysis. Venus has trace amounts of water vapor in its atmosphere, but extracting it requires processing enormous volumes of corrosive atmosphere. The energy requirements and technical challenges make water extraction on Venus orders of magnitude more difficult than on Mars. Soil availability matters more than you might think. Mars has regolith, loose rock and dust covering the surface. This material can be used for construction, radiation shielding, and potentially agriculture after treatment. Scientists have successfully grown plants in simulated Martian soil under laboratory conditions. Venus has no accessible surface material. Any construction material must be imported from Earth at enormous cost or somehow manufactured from atmospheric gases. Building large structures becomes prohibitively difficult when you cannot use local materials. The communication advantages of Mars deserve emphasis. Earth-Mars communication delay ranges from 4 to 24 minutes, depending on planetary positions. Challenging but manageable. Mars colonists could have delayed conversations with Earth. They could receive technical support during emergencies. Venus's thick atmosphere creates additional communication challenges beyond the 2 to 14 minute light speed delay. Radio signals must penetrate those dense clouds, limiting bandwidth and reliability. Career and life planning considerations favor Mars. A Mars colonist could reasonably expect to return to Earth if desired. The return journey requires waiting for favorable orbital alignment, but it's feasible with current propulsion technology. A Venus Cloud City colonist faces uncertain prospects for returning to Earth. The technical challenges of ascending from Venus's deep gravity well and thick atmosphere, then transferring to an Earth-bound spacecraft, exceed anything currently operational. The psychological dimensions of Mars settlement, while challenging, seem more manageable than Venus. Mars colonists would experience genuine planetary exploration. They could drive rovers, examine geological formations, search for fossils, and potentially discover evidence of ancient life. These activities provide meaning and purpose. Venus colonists would float in an eternal sky, unable to access the surface, unable to explore in any traditional sense. The psychological impact of permanent suspension without access to solid ground remains unknown but concerning. Medical considerations reinforce Mars' advantages. Mars's 0.38 Earth gravity, while lower than ideal, allows humans to walk normally with some adaptation. Bone density loss and muscle atrophy occur more slowly than in zero gravity. Exercise equipment can help maintain physical condition. Venus's 0.904 Earth gravity seems beneficial, but this advantage applies only if you're standing on something solid. Floating platforms would likely operate in microgravity unless artificially spun. Reintroducing the health problems Venus gravity supposedly solves, manufacturing capabilities on Mars could eventually support self-sufficiency. Iron, silicon, aluminum, and other useful elements exist in Martian rocks and soil. With sufficient energy and equipment, Mars colonists could manufacture metal parts, electronics, and construction materials. This path to self-sufficiency makes Mars colonization economically viable in the long term. Venus offers no equivalent resource base. Everything must come from Earth or be synthesized from atmospheric gases at enormous energy cost. The legal framework for Mars settlement is developing now. The Outer Space Treaty prohibits national appropriation of celestial bodies, but doesn't clearly address private settlement. International discussions about Mars resource rights, settlement governance, and property law are ongoing. This legal groundwork matters for attracting investment. Venus has generated no equivalent legal discussions because serious settlement plans don't exist. Educational institutions and research organizations are investing heavily in Mars-relevant research. Universities study Mars geology, Mars agriculture, Mars construction techniques, and Mars human factors. This research ecosystem creates jobs, attracts funding, and trains the experts who will support Mars missions. Venus research, by comparison, remains a niche specialization with limited career opportunities. This disparity becomes self-reinforcing. Mars attracts more researchers, generating more knowledge, making Mars missions more feasible, attracting more investment. The inspiration factor extends beyond public relations. Mars represents humanity's next frontier in ways that resonate deeply with human nature. We're explorers, we're builders, we push boundaries. Mars offers a new world to explore, new challenges to overcome, new communities to build. This narrative drives not just public support, but also the personal motivations of the scientists, engineers, and astronauts who dedicate careers to space exploration. Venus cloud cities, while technically interesting, don't tap into these fundamental human drives the same way. Emergency contingencies favor Mars substantially. If something goes catastrophically wrong at a Mars base, habitat breach, life support failure, medical emergency, rescue missions are conceivable. The Mars transit time is long but manageable. Equipment and supplies can be pre-positioned. Multiple agencies could potentially contribute to rescue efforts. Venus offers no such safety net. The transit time to Venus, combined with the technical challenges of accessing cloud cities, means help cannot arrive in time for most emergencies. This creates an ethical dimension to Venus colonization. Are we prepared to send people somewhere knowing we cannot rescue them? The cultural and historical legacy question matters for long-term thinking. Mars settlement would represent humanity's first permanent expansion beyond Earth. The first Mars colonists would be remembered for millennia. Mars would become humanity's second home, a new branch of human civilization. This legacy appeals to the deep human desire to be part of something larger than ourselves. Venus, even with successful cloud cities, would represent a technological curiosity, impressive but not transformative in the same way. Climate research provides another Mars advantage. By studying how Mars lost its atmosphere and water, we gain insights into Earth's climate system. The accessible geological record on Mars preserves evidence of this climate transition. This research has direct applications to understanding Earth's climate change. Venus's geological record, buried beneath crushing atmosphere and extreme heat, remains largely inaccessible, while Venus atmospheric research offers some climate insights. Mars provides more comprehensive data about planetary climate evolution. The stepping stone argument deserves consideration. Mars colonization develops technologies and operational experience applicable to more distant destinations. Living on Mars teaches us how to extract resources, maintain closed-loop life support, and build self-sufficient communities off-world. These capabilities enable eventual missions to Jupiter's moons, Saturn's system, or beyond. Venus cloud cities, being fundamentally different from any other planetary exploration scenario, don't provide transferable experience to other destinations. Resource extraction economics favor Mars decisively. Multiple companies are developing Mars resource extraction technology, water mining, regolith processing, metal extraction. These technologies have clear business models. Water extracted on Mars could fuel spacecraft, reducing the cost of Mars-Earth transport. Venus offers no equivalent economic opportunity. The resources available, atmospheric gases, have limited commercial value and require processing in one of the most hostile environments in the solar system. The final consideration is perhaps the most important. Mars is achievable with current technology and reasonable extensions of existing capabilities. The challenges are enormous, but not insurmountable. We know how to land on Mars. We know how to operate equipment there. We know how to extract resources. We know what habitats need to provide. Venus cloud cities require fundamental breakthroughs in multiple areas simultaneously. This difference between difficult and revolutionary defines the practical distinction between Mars and Venus as colonization targets. The technological timeline tells its own story. SpaceX announced plans to launch uncrewed Starship missions to Mars in 2026, with crewed flights potentially following within 4 years if those initial missions succeed. NASA targets the 2030s or early 2040s for human Mars missions. These aren't speculative fantasies. They're engineering projects with development timelines, hardware testing, and incremental milestones. The Starship development program demonstrates daily progress. Test flights happen, prototypes evolve, problems get solved. Venus missions. The Da Vinci mission launches in the early 2030s as a brief atmospheric probe. ESA's Envision follows in 2031. Both are reconnaissance missions, not colonization precursors. No one is building Venus habitat prototypes or testing cloud city technologies. The infrastructure gap widens with every passing year. Mars missions benefit from decades of accumulated knowledge. We've successfully landed multiple rovers. We understand the descent profile. We know what wheels work on Martian soil. We've tested power systems in the actual environment. The Perseverance rover carries technology demonstrators for future human missions. MOXIE produces oxygen from the Martian atmosphere, proving resource extraction works. Venus has no equivalent technology development path. Every Venus mission starts from scratch, fighting conditions that destroy conventional spacecraft within hours. Consider the sample return architecture. The Mars 2020 Perseverance mission represents the first step of a multi-mission campaign to bring Martian samples to Earth. Future missions will retrieve these samples and launch them back home. The engineering is complex, but understood. We know how to land on Mars. We know how to collect samples. We know how to launch from the surface. Venus sample return faces exponential challenges. How do you preserve samples at 450 degrees Celsius? How do you launch from an environment with 93 bars of pressure? How do you prevent contamination from sulfuric acid during collection. These aren't solved problems with development timelines. They're fundamental research questions. The economic argument increasingly favors Mars. Multiple companies are developing Mars resource extraction technology because they see business opportunities. Water mining has clear customers. Spacecraft needing propellant for the journey back to Earth. Metal extraction could supply orbital manufacturing. Regolith processing might provide construction materials. These business models attract private investment, accelerating development independent of government funding. Venus offers no equivalent commercial opportunities. Atmospheric gas extraction has limited market value. No one needs bottled Venusian carbon dioxide. The Cloud City concept generates tourism speculation, but tourism requires destinations people survive long enough to enjoy. Educational and inspirational value differs dramatically. Mars missions capture public imagination because people can visualize themselves there. Students watch rovers explore alien landscapes and think, I want to help send humans there. Mars science generates steady media coverage because rovers discover new things weekly. Each discovery builds momentum for the next mission. Venus struggles for attention. Atmospheric composition measurements don't generate headlines. The public cares about finding life or establishing new homes for humanity. Venus offers neither narrative. The international cooperation dimension matters for long-term sustainability. Mars exploration involves NASA, ESA, Roscosmos, JAXA, and emerging space agencies from China, India, and the UAE. This distributed effort creates redundancy and shared knowledge. If one program faces funding cuts, others continue advancing the field. Venus exploration depends primarily on NASA and ESA missions. The limited international involvement means Venus research remains vulnerable to single-point failures in funding or political support. Political considerations shape these decisions more than scientists prefer to acknowledge. Space programs require sustained political support across multiple election cycles. Mars maintains that support because the goal resonates with voters, humans walking on another planet. The Apollo program succeeded partly because the goal was clear and inspiring. Venus cloud cities fail that test. How do you explain to taxpayers why we're spending billions to float in sulfuric acid clouds instead of walking on solid ground? The political narrative for Mars writes itself. The Venus narrative requires constant explanation. The failure mode analysis reveals uncomfortable truths. Mars missions can fail gracefully. If one habitat module malfunctions, colonists have time to repair it or move to backup systems. Supply missions can bring replacement parts. Emergency evacuation, while difficult, remains theoretically possible. Venus cloud cities offer no graceful failures. A structural breach in a balloon habitat at 50 kilometers altitude means immediate catastrophic decompression into an atmosphere that will kill you in seconds. There's no walking to the backup habitat. There's no emergency landing site. You either maintain perfect system reliability or everyone dies. The medical dimension deserves scrutiny. Mars colonists face radiation exposure and reduced gravity health effects. These are serious challenges requiring mitigation strategies, radiation shielding, artificial gravity from centrifuges, intensive exercise regimens. But we understand these problems. Decades of space station research provide baseline data. Venus cloud cities introduce entirely new medical unknowns. What happens to human physiology living permanently in a balloon habitat subject to constant atmospheric turbulence? How does the body adapt to hurricane-force winds as normal conditions? What psychological effects emerge from never touching solid ground? We have no research framework for these questions. The construction sequence highlights practical differences. Building a Mars base follows a logical progression. Land cargo missions with supplies and equipment, deploy power systems and life support, construct habitats using local materials, establish greenhouse facilities for food production. Each step builds on the previous one. Crews can arrive after infrastructure is operational. Venus cloud cities require everything to work simultaneously. You can't stage construction. You can't test systems in the actual environment before sending people. The entire habitat must function perfectly from day one at 50 kilometers altitude in sulfuric acid clouds. There's no iterative development path. Communication delays affect operations differently. Mars communication suffers 3 to 22-minute light speed delays depending on orbital positions. This requires autonomous systems and pre-planned operations, but it's manageable. Venus has shorter communication delays due to proximity, but that advantage vanishes against other challenges. What good is faster communication if your equipment only survives hours? Mars rovers operate for years precisely because reliable communication enables remote troubleshooting and adaptive planning. The energy equation favors Mars despite Venus receiving more sunlight. Yes, Venus gets 4 times the solar energy at cloud-top altitude, but Mars offers nuclear power options. Reactors work regardless of dust storms or day-night cycles. Solar panels on Mars produce reliable power with predictable degradation rates. Venus cloud cities face unique power challenges, maintaining solar panel orientation while buffeted by hurricane winds, dealing with sulfuric acid corrosion, managing power systems during Venus's 243-day rotation period. These aren't insurmountable obstacles, but they add complexity without providing commensurate advantages. The psychological research from extreme environment analogues suggests Mars colonization remains within human behavioral tolerances. Antarctic stations, submarine deployments, and space stations all provide data points. Humans can adapt to isolated, confined environments if they retain some connection to familiar patterns. Solid ground underfoot, a visible horizon, the ability to go outside with proper protection. Venus cloud cities remove all these anchors. You're permanently suspended in opaque clouds, never seeing the surface or stars, feeling constant turbulence, knowing the outside environment will kill you instantly. The psychological burden may exceed human adaptability. The governance and legal frameworks being developed assume solid planetary surfaces. The Outer Space Treaty and subsequent agreements address territorial claims, resource extraction, and environmental protection in ways that map to traditional concepts of land and borders. Mars fits these frameworks. You can claim to have explored a region, established a settlement, extracted resources from specific locations. Venus cloud cities exist in 3-dimensional atmospheric space. with no fixed reference points. How do you establish territorial claims? How do you prevent collisions between different nations' floating habitats? The legal ambiguity isn't fatal, but it adds another layer of complexity. The backup system philosophy differs fundamentally. Mars bases can be designed with redundant modules spread across a settlement. If one habitat fails, you evacuate to another. Multiple power systems provide backup. Supply caches can be distributed across the landing site. Venus cloud cities must keep everything in the air simultaneously. You can't have a backup habitat on the surface. You can't cache emergency supplies on the ground. Everything required for survival must float at the same altitude, subject to the same atmospheric conditions, vulnerable to the same failure modes. The children question haunts Venus colonization advocates. Can humans reproduce successfully at reduced gravity? Mars is 38%. Earth gravity raises concerns, but Venus's 90% gravity should be adequate. Yet Venus cloud cities introduce other reproduction questions. Can fetuses develop normally in constant atmospheric turbulence? What happens to infant development without access to solid ground for crawling and walking? These aren't hypothetical concerns. They're fundamental questions about whether Venus colonization could ever become truly self-sustaining rather than requiring constant resupply of people from Earth. The agricultural dimension demonstrates practical advantages of solid surfaces. Mars greenhouses can use local regolith as growth medium with added nutrients. Water ice provides irrigation. Transparent domes offer radiation shielding while admitting sunlight. Gravity helps with water distribution and root development. Venus cloud cities require hydroponics or aeroponics. Everything suspended, nothing touching ground. These systems work on Earth and in space stations, but they're energy intensive and complex. They require perfect maintenance because crop failure means starvation, with no backup except supplies from Earth. The manufacturing question reveals practical realities that Venus advocates rarely address. Mars settlements can establish workshops using local materials. Martian regolith can be sintered into bricks using solar concentrators. Metal extraction from iron-rich soil is feasible with established metallurgical techniques. You can build replacement parts, repair equipment, eventually manufacture entire structures using resources extracted from the ground beneath your feet. Venus cloud cities depend entirely on materials brought from Earth or possibly extracted from the atmosphere through complex chemical processing. Must either arrive from Earth or be manufactured in facilities that themselves must remain suspended in the atmosphere using materials that originally came from Earth. The supply chain never closes. The cultural narrative matters more than engineers typically acknowledge. Humans tell stories about frontiers, about planting flags and walking on new worlds. Mars fits that narrative perfectly. You can imagine stepping off a lander onto red soil, taking those first steps, looking at mountains and valleys and ancient riverbeds. You can envision future colonists hiking across valles marineris, drilling into polar ice caps, discovering fossils in sedimentary rocks. Venus cloud cities offer no equivalent imagery. You float in opaque yellow-brown clouds, never seeing stars or surface, experiencing constant turbulence, knowing you're suspended over a hellscape that would vaporize you instantly. It's a harder story to tell, a less compelling vision to inspire the decades of effort and trillions of dollars required for planetary colonization. The contamination protocols differ fundamentally. Planetary protection requires we avoid contaminating Mars with Earth life before we can determine whether Mars ever developed its own biology. This creates restrictions on where we can land, how we must sterilize equipment, what precautions we must take. These restrictions are manageable because Mars's surface is accessible and diverse. We can choose landing sites that balance scientific interest with contamination risk. Venus's surface remains largely unexplored, precisely because nothing survives there long enough to conduct detailed surveys. The cloud layer, where colonies might float, exists in a region where contamination concerns are minimal because the environment is so hostile that Earth organisms couldn't possibly survive unprotected. Venus thus offers fewer planetary protection constraints. But this advantage stems from the same extreme conditions that make colonization impractical. The economic model for Mars colonization at least has a theoretical foundation. Initial settlements would require massive investment with no immediate return, but eventual self-sufficiency becomes plausible. Mars colonists could manufacture fuel, grow food, extract water, build habitats, potentially export rare minerals, or serve as a way station for asteroid mining operations. The path from subsidy-dependent outpost to economically viable settlement is long but conceivable. Venus cloud cities face a different economic reality. They would require continuous resupply from Earth indefinitely. The atmospheric resources available, carbon dioxide, nitrogen, trace sulfur compounds, have limited commercial value. You can't export clouds. There's no Venus equivalent of rare Earth minerals or water ice. The economic justification relies entirely on scientific research or maintaining a human presence for its own sake. Both noble goals, but historically insufficient to sustain large-scale colonization efforts without additional practical benefits. The scaling question demonstrates fundamental differences in growth potential. Mars settlements can expand across the surface, establishing multiple bases in different regions to access diverse resources and environments. You can have a polar base for water ice extraction, an equatorial base for easier launches to orbit, a base in Valles Marineris for geological research. Each base operates independently with its own life support, power systems, and food production. Venus cloud cities must remain suspended at roughly the same altitude to maintain survivable conditions. You can't have a base on the surface for backup. You can't establish outposts at different atmospheric levels because the conditions become lethal above or below the narrow habitable band. All expansion must occur horizontally within the cloud layer, with every new habitat facing identical challenges and requiring identical ongoing support. The research that actually drives mission selection reveals institutional priorities. NASA's Mars exploration program has operated continuously for decades with clearly defined objectives. Understand Mars's climate history, determine whether life ever existed, prepare for human exploration. This program generates predictable funding requests, develops technologies with obvious applications, and produces results that justify continued investment. Venus research lacks this programmatic coherence. Venus missions compete individually for funding against Mars orbiters, Mars rovers, Mars sample return, and Mars human exploration studies. Venus advocates must argue for each mission separately, while Mars benefits from institutional momentum. This isn't necessarily fair or scientifically optimal. It reflects how space agencies actually function. The public engagement dimension influences long-term political support. Mars missions generate consistent public interest because they return images people can relate to. Landscapes that look almost Earth-like despite the alien sky. Dust devils crossing plains, layered rocks revealing geological history. The Perseverance rover's video of its sky crane landing went viral because people could understand what they were watching. Venus missions can't provide equivalent engagement. Spacecraft descending through opaque clouds transmit sensor data and brief surface images before failing. The science is valuable but difficult to communicate to non-specialists. This engagement gap translates directly into political support. Congressional representatives respond to constituents excited about Mars rovers. They're harder to convince about Venus atmospheric probes that collect data most people can't interpret. The SpaceX factor changes Mars colonization from theoretical possibility to active development program. Whether or not Starship achieves its ambitious timeline, the company is investing billions in technologies explicitly designed for Mars transportation. Raptor engines burn methane and oxygen, propellants that can be manufactured on Mars. Starship's payload capacity and refueling architecture assume planetary surface operations. This private sector momentum creates infrastructure that government programs can leverage. Venus has no equivalent advocate. No company is developing Venus-specific transportation systems because the use case remains speculative. The Cloud City concept, however elegant theoretically, hasn't attracted the engineering investment required to make it practical. The radiation shielding advantage Venus offers proves less significant upon detailed analysis. Venus's upper atmosphere provides Earth-like radiation protection, while Mars's thin atmosphere offers minimal shielding. This initially suggests Venus superiority, but Mars colonists can shield themselves using the planet's mass, underground habitats, hills of regolith piled over structures, caves, and lava tubes that provide natural protection. These solutions use local materials and proven techniques. Venus cloud cities require active shielding or thick structural walls, both of which must remain airborne. The engineering to keep radiation shielding suspended in the atmosphere may actually prove more complex than simply burying habitats in Martian soil. The comparative planetology argument supports studying both worlds, but it doesn't equate to colonizing both. Understanding why Venus suffered runaway greenhouse warming while Earth maintained habitable conditions provides crucial insights for climate science. Studying Venus's atmospheric chemistry, cloud physics, and surface-atmosphere interactions advances planetary science. These research objectives don't require permanent human presence. Robotic missions, atmospheric probes, and orbital surveys can answer most questions about Venus's evolution and current state. Mars research benefits from human presence because understanding whether life ever existed there may require on-site laboratory analysis, adaptive investigation, and the ability to explore diverse locations. the scientific case for human Mars exploration exceeds the case for Venus colonization. The timeline for achieving either goal reveals practical priorities. Mars human missions could occur within 15 to 20 years, given sufficient funding and political will. The technology exists or is under development. Heavy lift rockets, deep space habitats, life support systems, surface rovers, in situ resource utilization. The challenges are primarily engineering and logistical, rather than requiring fundamental breakthroughs. Venus cloud cities require technologies that don't exist and may require decades to develop. Materials that resist sulfuric acid corrosion while remaining lightweight. Balloon systems that maintain altitude through hurricane winds. Closed-loop life support with no surface backup. Power systems that function reliably in Venus's unique conditions. The development timeline stretches beyond current planning horizons. Mars wins this comparison not because Venus is impossible, but because Mars is practical. The red planet offers accessible science, manageable engineering challenges, psychological sustainability, economic potential, and alignment with how humans naturally think about exploration and colonization. Venus's theoretical advantages, better gravity, superior radiation protection, more frequent launch windows, don't overcome the fundamental problem that you're asking humans to live permanently suspended in corrosive clouds above a hellish surface they can never visit. The dream of cloud cities floating through Venus's atmosphere remains science fiction, not because the engineering is impossible, but because the practical alternatives are simply better. When humanity takes its next giant leap beyond Earth, we'll take it on solid ground under a butterscotch sky, walking across ancient riverbeds on Mars, rather than floating forever through the sulfuric haze of Venus. The comparison ends where it began, with a choice that seems counterintuitive until you understand what's actually being chosen. Venus offers proximity, similar size, Earth-like conditions at cloud level. Mars offers distance, smaller scale, hostile surface conditions. Yet every calculation, every engineering study, every funding decision points the same direction. This isn't about picking the easier target. Mars presents extraordinary challenges. The radiation alone requires solutions we're still developing. The distance means communication delays that complicate every operation. The cold threatens equipment constantly. The dust infiltrates everything. Building a sustainable settlement that will test human ingenuity to its limits. But those challenges have solutions. Radiation shielding uses mass, regolith piled over habitats, underground construction, natural lava tubes. Communication delays require autonomy in systems and decision-making, which we're learning to provide. Cold is manageable with insulation and power systems we understand. Dust requires engineering attention, but not revolutionary breakthroughs. Each problem has a solution path we can trace from current technology through incremental improvements to working systems. Venus's challenges don't work that way. The surface temperature doesn't have an engineering solution. It simply destroys anything conventional. The atmospheric pressure isn't something you shield against for extended periods at those temperatures. The sulfuric acid clouds don't become less corrosive through clever design. These aren't problems requiring better engineering. they're fundamental environmental constraints that dictate entirely different approaches. The cloud city concept tries to sidestep these constraints by avoiding the surface entirely. It's elegant in theory. The physics genuinely works. Breathable air floats in carbon dioxide, creating natural buoyancy at altitudes where temperature and pressure become survivable. But elegant theory encounters practical reality when you ask how humans actually live there, how they access resources, how they expand beyond initial habitats, how they become self-sufficient rather than permanently dependent on Earth. Mars offers something Venus cannot: a pathway from initial outpost through expanding settlement to eventual self-sufficiency. The first Mars base will be entirely dependent on Earth, certainly, but each mission can build on previous infrastructure. Equipment doesn't melt after hours. Solar panels keep generating power for years. Habitats remain usable. Water ice can be extracted and stored. Food production facilities can expand using local resources. The progression from dependence to independence is long and difficult, but traceable. Venus cloud cities remain perpetually dependent. Every structural component must be imported or manufactured from atmospheric gases using complex chemical processing. Every meal requires either resupply from Earth or perfect functioning of suspended hydroponic systems with no backup. Every equipment failure requires replacement parts from Earth because there's no ground-based mining or manufacturing. The settlement never closes its supply loop because the fundamental resources don't exist in accessible form. The human factor compounds these practical considerations. People need more than survivable temperature and pressure. They need solid ground, access to resources, ability to expand and build, connection to place that comes from standing on a surface rather than floating above it. Mars provides these psychological anchors. Venus removes them entirely. The funding decisions reflect these realities. When NASA evaluates planetary missions, when Congress approves budgets, when private companies invest in space technology, they're answering a question beyond pure science. Where can humanity actually go? Not just visit briefly, but establish permanent presence. Mars answers that question. Venus doesn't, at least not with any technology we have or can foresee developing within relevant timeframes. SpaceX's Starship development, NASA's Artemis program, international cooperation on Mars missions, private sector investment in Mars resource extraction. All of this momentum points one direction. It's not that scientists have stopped caring about Venus. The Da Vinci and Envision missions prove continued interest, but interest in studying the planet differs fundamentally from commitment to colonizing it. The sample return architecture illustrates this distinction perfectly. Mars sample return is in active development because we can land, collect samples, launch from the surface, and return to Earth using technology we understand. Venus sample return remains theoretical because every step presents extreme engineering challenges without clear solutions. The difference isn't difficulty, but kind. Mars is hard. Venus requires breakthroughs we can't schedule. The timeline speaks volumes. Multiple Mars missions operate currently. More are launching soon. Human missions have target dates in the 2030s, backed by hardware development and mission architecture studies. SpaceX aims for uncrewed Starship landings in 2026. These aren't fantasies, but engineering programs with test schedules and incremental milestones. Venus has 2 reconnaissance missions planned for the early 2030s. No habitat prototypes exist. No companies are developing Venus-specific technology. No space agency has proposed human Venus missions with actual timelines. The contrast isn't subtle. It's the difference between active colonization, preparation, and basic scientific investigation. Mars won this competition decades ago, when the first rovers survived beyond their planned lifetimes and started sending back data that inspired the next generation of missions. Each success built momentum that Venus couldn't match, because Venus missions don't survive long enough to generate that virtuous cycle. The Spirit rover's 6-year mission told scientists where to send Curiosity. Curiosity's discoveries inform Perseverance's target selection. Perseverance's sample collection sets up future return missions. The progression is clear and cumulative. Venus missions remain episodic. Each one solves survival challenges independently without building toward longer duration capabilities, because the fundamental environment doesn't permit it. You can't incrementally improve from 2-hour survival to 2-day survival when the physics of the environment destroy conventional materials regardless of how well engineered they are. The question isn't whether Venus is scientifically interesting. It absolutely is. The question is whether it's a viable colonization target given alternatives. When you have one planet where rovers operate for years, where water ice is accessible, where habitats can be built using local materials, where solid ground permits walking and construction, and another planet where everything must float in corrosive clouds above an inaccessible hellscape, the choice becomes obvious. Mars isn't perfect. The low gravity raises health concerns we're still studying. The radiation requires serious mitigation. The distance complicates logistics. The cold and thin atmosphere create constant engineering challenges. But these challenges exist on a spectrum from difficult to very difficult, not from difficult to physically impossible. Venus's challenges exist in a different category. You cannot walk on the surface in any suit we can conceive building. You cannot access the ground for resources. You cannot expand settlements using local materials. You cannot establish agriculture in soil. These aren't engineering problems requiring better solutions. They're fundamental constraints that dictate entirely different approaches to human presence. The Cloud City advocates have a point about Venus's advantages: better gravity, superior radiation protection, more frequent launch windows. These are real benefits, but they don't overcome the fundamental limitation that you're asking humans to live permanently suspended in an atmosphere they can never leave, above a surface they can never visit, dependent on supply chains stretching back to Earth with no path to self-sufficiency. Humanity's expansion into space will follow the path of least resistance toward genuine sustainability. That path runs through Mars, not Venus. The red planet offers solid ground, accessible resources, manageable challenges, and a progression from outpost to settlement, to self-sufficient civilization. Venus offers an engineering curiosity, impressive if achieved, but not transformative for human civilization's future. The choice was never really between Venus and Mars. It was always between floating forever in clouds or walking on new ground, between permanent dependence or eventual independence, between a technical achievement or a new home. Mars is where we're going because Mars is where we can actually build something lasting. Venus will remain what it's always been, a fascinating neighbor we study from a distance, not a destination where humanity plants roots.